Hi, everyone. I'm Josh Do. I'm very glad to be invited to give a presentation about the FMT model-based design Autopilot project, which is powered by Autostrat, and I'm the author of the FMT project. So here is the content of the presentation. First, for the introduction, what is FMT? FMT is also known as Firmware Autopilot. It is the first open-source autopilot system based on model-based design method, which is the main difference compared to other autopilot systems. MBD is a very powerful tool and is widely used in aerospace and automotive field. Based on MBD, FMT can be used to quickly build control system for not only drones, but also for boats, cars, or even robots. FMT is a relatively new project as it became public last year. It began from my hobby project, Autopilot, back to 2016. It was one of the first open-source flight control systems which used Autostrat. FMT is evolved from Autopilot, so it also used Autostrat compared to some other well-known open-source autopilot systems. PS4 use NotX, and Autopilot or APM use ChibOS. So if you know Autostrat before, FMT would look quite familiar to you, and it would be much easier to use compared to PS4 or APM. We believe that a good system should separate embedded software from the algorithms and integrate with a 3D simulation environment, which is a future, I think. So embedded software developer and algorithm developer can focus on their own area. Based on this idea, FMT is separated into three components. First one is FMT-Firmware, which is the embedded system developed with C language. It contains the core software framework, such as drivers, middleware, top-level tasks, and so on. The first figure here shows the console provided by FMT firmware. It provides lots of powerful commands to interact with the system. The second component is FMT-Model, which is the modeling framework which built in MATLAB. It contains algorithm and simulation Simulink models, such as inertial navigation system, also known as INS, a control model, a state machine, or also called a flight management system, plant, and so on. The second figure shows the mirror simulation built in FMT model. You can run the model in Simulink and see the simulation data, as well as 3D visualization in the real time. The last one, FMT Sim, is still under developing. It is a simulation environment based on advanced 3D engine such as Unreal. The goal of FMT Sim is to provide a realistic simulation environment with rich test things, which will make great convenience for testing. The last figure shows the hero simulation using FMT and Unreal. It can be operated like a real drone, and as you can see, the rendering, in fact, is quite nice. In a word, FMT builds a software platform that integrates embedded software, modeling, and 3D simulation altogether. The first design goal of FMT is to create a lightweight, efficient, and stable embedded system, which is FMT firmware. The second goal is that FMT is designed for MBD. So in order to achieve that, the FMT firmware provides several modules, such as log system, parameter system, and also the IPC system to support the development of the MBD. Also, the FMT model provides a platform to design and simulate your model. The last goal is to use advanced simulation technology to build a powerful simulation environment, which is FMT Sim. For this section, I will introduce the software architecture of FMT firmware and FMT model. First, this is the architecture of the FMT firmware. The lowest layer is target hardware, which contains the MCU, peripheral drivers, and board related files. FMT currently supports various hardware such as PTOC, PTOC 4, CUAV V5 Plus, and Cube Orange. So if you want to port FMT to a new hardware, you have to implement this layer by yourself. FMT also supports QEMU, so you can run FMT on your PC without need of a real board. We expect that FMT will support more hardwares in the future, which need help from the community, which is you. The driver layer contains I/O device driver, such as sensors, onboard chips. The hell layer isolates the upper layer with the driver layer, so it makes porting easier. And also we can move the common driver code to hell layer, which simplify the driver development. And the autos layer is Autopilot. And now we are using a version 4.0.3, and in the future we may upgrade to the latest version. Modules layer contains various powerful components, such as MuMCM, which is the IPC module based on subscribe and publish model, as well as log system, parameter system, control system. The mob proxy provides the ability to communicate with a ground control system, such as Q-ground control, via the Mavlink protocol. The models layer includes algorithms. As you can see here, we have 4 kinds of algorithms. The INS, which is also known as Inertial Navigation System, controller, FMS, Flight Management System, which is also known as State Machine, and the plant. The algorithm can be the C or C++ code generated by Simulink model, or the handwritten code. For instance, now FMT contains 2 INS systems. One is base FMS, which is created in Simulink and generate C code to integrate into FMT firmware. The other one is the PS4 EKF INS system, which is written by C++. Now is perfectly ported into the FMT platform. The top layer contains several tasks. Each task corresponds to a specific functionality. For example, task vehicle runs the algorithms to control the vehicle. Task COM takes the responsibility to communicate with the ground control system via the Mavlink. You can also enable or disable some tasks, or just create new one by yourself to customize your system's functionality. The next one is the architecture of the FMT model, which is a key to support the MBD. Firstly, we create FMT toolbox, which contains lots of useful blocks to speed up your model design, such as mass, quaternion transformation. The other benefit of it is that FMT toolbox is totally built with Simulink base blocks, which means you don't have to buy other commercial toolbox. The simulation model implements a MIL and open loop simulation model, which enables you to do the MIL and open loop simulation. In the future, we may implement more simulation model. The other most important one is the algorithm library, which contains 4 kinds of algorithms that we mentioned before. Each kind of algorithm contains 1 or more models. For example, INS could have a complementary filter model or an extended Kalman filter model. Controller could also have controller for drones, car, boat, or even for robots. The idea here is that by selecting the specific algorithm model or create a new one by yourself which meets your requirements, you can quickly build the control system for any vehicle using the FMT. It is very important to create the algorithm library because we can share our work and also reuse the work from others. In this case, FMT is just a platform to host various algorithms. Okay, so what is the model-based design? The definition is that a model-based design is a framework used in virtual prototyping of embedded software. MBD has evolved to overcome various difficulties and complexities that typically arise during the design life cycle of embedded software for closed-loop control system. In a simple words, MBD refers to an algorithm model built using MBD design software such as Simulink. Through graphical and code automatic generation. As shown in the diagram below, we use Simulink math blocks to build up our algorithm. We first do the simulation to verify it works. Then we can generate C or C++ code to integrate into an embedded software system. So why use MBD, or what's the pros and the cons? In my opinion, I think MBD has the following advantages. First, graphical programming to improve the development efficiency. Secondly, easy maintenance and modify. Also, models are more reusable. A powerful simulation ability, such as mirror simulation and open loop simulation, which we will introduce later. To improve the debug and optimization efficiency. Fourthly, automatic code generation to reduce errors due to the handwritten code. Lastly, strict modeling specification. For example, for Simulink, it has lots of check for models, so which can generate a more secure system which has better security. Regarding to the disadvantages, also I list some here. First, less flexibility than coding. For example, C and C++, we can use pointer as we want everywhere, but for Simulink, we cannot use pointer. Secondly, a few mature MBD development tool, for example, Simulink, which is normally very expensive. Also, the model file is binary. Yeah, so we cannot use gitdiff, which will be a problem if we have several people to work together with a same file. But there is also some tool can help that, but normally you have to pay that also. Last one is that generated code has lower efficiency. Here I will give a big question mark here. Since based on my experience, the Simulink generated code is more efficient than most programmers and slightly less efficient than experienced programmer. So do not worry about it. Do not worry about the auto-generated code efficiency, and it's usually more robust than handwritten code. FMT supports various of simulation methods, such as mirror model-in-a-loop simulation, open loop simulation, software in a loop, hardware in a loop, and also software in hardware simulation. Here I want to introduce them all. For more information, you can check FMT user guide. Here, I would like only to introduce mirror simulation and open loop simulation because they are very important and useful for MBD. So first for mirror simulation. Mirror simulation, also known as model-in-the-loop simulation, provides an efficient way to test your algorithms. It can avoid applying algorithms directly to a real hardware, which possibly become a disaster. As shown in the diagram here, the mirror simulation includes a planned model, which accepts controller's output and generates the vehicle states, such as altitude, attitude, velocity, position, as well as sensor data for NS to do the data fusion. We can send the vehicle states to virtualization blocks such as MATLAB 3D, Unreal Engine, or Gazebo, whatever you like. And we can connect our remote controller to generate pilot command to control the vehicle. The biggest benefit for mirror is that we can test our algorithms in a very early stage and easily get all the simulation data for analyze purpose. It's a very cheap way to test and improve your algorithm. So we notice that the mirror simulation result is usually not the same as the real test result, because it depends on whether your planned model is accurate enough or not. So mirror simulation is not good at tuning your controller's parameter, such as PID, but it's very useful to optimize and test the model for NS, FMS, and so on. Here is the mirror simulation model, which is designed with the Simulink. It is quite similar to the diagram showed before. The FCS block here, it contains MS, FMS, and controller model inside. And here is a demonstration of mirror simulation. Here we connect a remote controller to send the pilot command to control the drone. As we can see, the 3D virtualization and simulation data in the real time. The other very useful tool for MBD is the open loop simulation. Open loop simulation provides the functionality similar to a black box. We only need to record a small amount of model input data. By recording it, we can run the open loop simulation, and we can get all the data information of the model, includes output data and also all the internal signal data, which is quite useful for us to solve the bugs and also to optimize your algorithm. This is the FMT open loop simulation model. The blocks inside the green areas, like here, and here, they are all data parsed from log file. For example, the data in the upper right corner, the NS out, FMS out, and control out. They are not used for simulation as it doesn't connect to any model. It is recorded only because we needed to compare with the simulation model output. For example, you can compare the recorded INS out with the simulation INS out result to check if they are identical. The consistency of the real test with the simulation result is very important. Ideally, it should be 100% identical. since it has the same input data and the algorithm is the same also, because the algorithm runs in the hardware is generated by the Symlink. So in theory, they should get the same result. But in practice, it's normally very hard to achieve that, because limited by the embedded system's real-time performance and also the data logging bandwidth. However, FMT can ensure the open-loop simulation result is almost 100% identical with the real test result, which means you can really trust your open-loop simulation result. Here is a test result. The blue lines are real test results, and the red lines are simulation results. As you can see, they fit perfectly. This is because FMT has great real-time performance and efficiency to achieve that. Okay, the next section I will present some test videos of FMT. All the algorithms are developed in Symlink and generate code to integrate into the embedded system. This is the outdoor position hold and maneuver flight test. As you can see, the drone can hold its position very nicely. This is a test for auto takeoff and landing, and also return home. This is the mission mode test to fly the waypoints created by Q-ground control. Let's play the video. First, we will start up our FMT firmware, and then it will connect to the Q-ground control automatically. Here we can set up the waypoints in the QGC and upload it to the embedded system. Then we can start mission. The drone would first take off to the target height, which is 10 meters. Then fly to the first waypoint, which is number 2 here. Then fly to the next one. At any time, you can click pause button to stop the mission, and then continue it. Also, you can set the mode to hold to pause the mission, and then send mode back to mission to continue. Okay, then fly to its last waypoint, number 4. When finished all the waypoints, it will return to the home position and then landing. Now landing. Okay, now altitude is 0, which means it reached the ground. So that's it. Okay, for the last section about the future of the project, here is the roadmap for this year. The first goal is to build the community, because FMT is the relatively new project. So we need to improve our document first, and then we will spend more time to help FMT developers and user as well. Secondly, for FMT firmware, we will continue to do the code mature to improve the code quality. Also, at this year, we have planned to support ROS or micro ROS, and also to support more hardwares. And also for port PS4 and APM algorithm, now we have already port PS4 EKF algorithm to FMT platform. In the future, we want to port more, such as control algorithm to support more vehicles, such as fixed wing, VTOL, and so on. For FMT-Model, in a part of optimize current models, we plan to develop more algorithms, such as the algorithm model for fixed wing, car, and also for boat. FMT Sim is also a very important topic for this year. We plan to create a 3D environment based on Unreal, which supports various vehicle simulation, and also which contains several lots of vehicle 3D model. So that's the roadmap. For the future of the project, FMT will always remain open source, and it is committed to become a universal platform for unmanned control systems. Not limited to drones, I hope FMT would be able to use for car, boat, robots, and so on. So in order to achieve that, we really need help from the community to contribute more algorithms model and help us to build a more flexible and reliable embedded system. So a big welcome to join us. FMT is still a baby. It needs more support and contribution to grow up. So if you are interested about it, you can get the code in the GitHub and also document as well. And here is the link. Yeah. Okay. So that's all for today. Thanks for listening. Bye.